So in the last video, I introduced, or at least talked about, the Gram-Schmidt theorem. I didn't prove it. I haven't even used it yet. So I immediately started talking about Gram-Schmidt, but then said, well, we need to go back and we need to learn a little bit more about something called the Kronecker delta, and how we're going to use that in our inner products. So there's a little bit more information we need before we actually get to actually using Gram-Schmidt. And that is something called the dual space. So basically, where I ended up last time was saying we could think about the vector spaces as geometric vectors. We could think about the vector spaces as numbers. We can also think about them as row and column vectors. So row and column vectors are a really nice way of thinking about vector spaces because it kind of gives you an easy example of taking an inner product, how it's like the dot product. But so I wanted to explore that a little bit more and remind you of some of the matrix manipulations you would need to do if you're using row and column vectors. So say you had a column vector, we'll call it B, which has coefficients b1, b2 to bn. So there's something called the transpose of a matrix. And what the transpose does is it reverses the row elements and puts them into column elements, and vice versa. And so since we're just using a single column vector, then doing the transpose of it, it has the symbol of a capital T. So B, the transpose of B, is a row where now all the elements are inside that row. B1, B2, all the way to Bn. Okay. Now, this is a course in quantum mechanics, so the transpose really just is good for real numbers. What we would really like is take the transpose of complex numbers. And so that's something called the adjoint. So the adjoint is doing two things. It does a transpose, and then it takes the complex conjugate. So therefore, if I take the adjoint of my vector B, and now it's not a T, but a little dagger symbol. So the adjoint is this dagger. So that makes the transpose. So I take my column vector B and turn it into a row vector, and I take the complex conjugate of each element. Like so. And so this is going to be, now we're just getting basically a different language. We're using the language of matrices and linear algebra to talk about our vector spaces, that we're going to be using bras and kets, and the bra is, basically an adjoint of the ket. So if we think about it a little deeper, then I seem to be biased toward the column vector. So all of my kets I seem to write as columns, and all the bras I write as basically the adjoint of those columns. To come up with complex row vectors. But that's kind of it's kind of a bias. I could instead consider viewing the world as all of the bra vectors are just normal rows, and then if I want to create a ket, the ket then is the adjoint of the row. So, I mean, it's kind of a subtle mathematical or philosophical point in the fact that, we want to start defining physical systems, and we want to represent them by these bras and kets. And so, my bias is to start defining them with the ket, and then take the adjoint and create a bra out of that. You could just as easily think of the universe in terms of in terms of bra vectors, and then take the adjoint, and then you've got the ket. But basically, what Dirac is telling us is that there is this dual space where no matter how you think about it, for every ket, there is a bra. Or for every bra, there is a ket. And so no matter how you think about it, you can always kind of flip back and forth between those 2 points of view. That you can, that if you have a ket, you can take the adjoint and find out what the bra is going to be, and then you've got this complete system. Now you've got a complete system where you can take, just starting with the ket, you can create the bra. You can take the bra and the ket and make the norm, and you can go crazy from there. So just a kind of a subtle mathematical point, but I wanted to bring it up to emphasize basically how we're organizing our description of the universe.